All right, so if Meredith comes in and has something to say, we'll pause and do that, but let's just start. So this is calc-based physics. I'm going to spend at least half the class today just going over the syllabus and the structure of the class. This is so annoying. Bye. You're looking at the back of that screen. Okay, we're going to go through the syllabus, and then the next thing I'm going to do is give 2 semesters of calculus over the span of 50 minutes or something, like my calculus bullet points kind of thing, and then we'll get into physics from there. But I think it helps for the way we're going to use calculus, which is not a lot of complicated calculations, really, the way that you do in a calculus class, but having a good overview of what's going on, how the calculations will be simple, but what's important is sort of the overall understanding. So that's what I'm going to try to talk about. The time commitment for this class, hold on. Okay, time commitment. 2 M's?
Yeah.
2 M's, 1 T. Time commitment. Well, and then another T later. If you Google like study time or time commitment or whatever for a college class, just punch it into Google. You can try it yourself. You don't have to trust me. Hey, Meredith.
I had a question from Young yesterday about.
So yeah, if you Google time commitment whatever for a college class, you'll get 1 million hits. I don't know about 1 million, but several hits. One will come from Harvard, one will come from SMU, one will, all over, all these totally different places with totally different student populations, but they all say the same thing. They say that for every credit hour, every credit that the class is, you should be doing 2 hours outside of class. Okay, so well, they really say 2 to 3, but I'm just going to say 2. Okay, if you do 2, I'll be happy and things will go well. Okay, so this is a 4-credit class. It's 5 credits. So I'm going to go through the calculation. 5 credits minus the 1 credit that the lab is. So there's a lab on Fridays. So let's say we're starting with a 4-credit class. And so 2 times 4 equals 8 hours a week outside of class. So that's about equal to 1 hour and 10 minutes a day. 7 days a week. Okay, so that's basically the idea. Maybe some people can get away with a little less than that. Some people might have to spend a little more than that, but that's basically what you're signed up for in this class. That means, so I'm saying this, I think it's important to say this to you guys because I know you have just a crazy busy schedule. I know you do. I remember that from last year. Most of you are doing things outside of class, and you're doing tons of credits with hard classes, AP classes, whatever. But this is about what it's going to take for this class to go well. Okay? And I think if you do this, this class will go really well. If you think like, okay, I'm busy right now until state whatever is done, and then I'll catch up or whatever. Historically, things go pretty badly if you think about it that way. You know what I mean? So, All right. Any questions about that? So that means so this is 110 a day, 7 days a week. So if you do it every other day, that's 2 hours and 20 minutes every time you devote to this class. If you go on a week-long vacation, that means you're going to have 8 hours of catch-up to do when you come back, of additional stuff. You know what I mean? All right. So I want to go through the syllabus first, just talk about the structure of the class. You all know how to get onto D2L? You use D2L in your other classes? Okay, so when you get into D2L, you see something like this. Maybe a little different because this is the instructor version, but it lists your classes over here on the right. So go into physics. Whenever I make changes to the class, changes to the problems, information about what topics are going to be on the tests and that kind of thing, it's going to be under the announcements. So first, just get in the habit of checking that regularly. But most of the stuff you're going to need is under materials content. And there are a few categories. More of these are going to be added as we go. There's going to be a lab category when we get to that. But course information has the syllabus in it. If there are any handouts with like formula sheets and stuff like that, this is where things like that will go. And then there are homework problems. So the homework problems, these are all the problems that your assignments are going to come from. So every day after class, I'm going to say, for Tuesday, January 10th, your assignment is from the calculus set, numbers 1 through 8 or something. You know what I mean? So these are all the problems. And most of those problems have solutions. I haven't given all the solutions because I want you to work through some without having access to those. But I think probably 75% of them or something over the course, you'll have access to full solutions. You can look at those as you're working on the problems. Although I would definitely recommend trying to do it without the solutions first and then looking at the solutions to get a sense of are you on the right track or not, or to give yourself hints and that kind of thing. Okay, so like for this calculus set, the only solutions I've posted so far, you have solutions to the first, the third, the fourth, the fifth. It's just missing ones every once in a while that you have to do on your own. But you can use this to make sure that you're on the right track as you work through them. And I won't be able to do every question that there are no solutions posted for in class, but if you come the next day and there's some you couldn't figure out how to do, I can always start the class by working through a problem or two. Okay. For now, what we want is the syllabus, so that's under course information. That's my name, Guy O'Lakin. My office, you probably don't need to know my office, but it's on the second floor in the science area, kind of just up the stairs from where we're going to do our labs. The best way to get in touch with me is email, but I can get back to phone calls too. But I'll never pick up the phone when you call because I don't have a phone in my office. So I get like an email that says someone called and it left a message, and then I can listen to the message and call back. But the quickest way is email. And office hours, I have my Normandale office hours during the day, but those probably won't be so useful to you. But I'm also doing 2 office hours a week at the high schools. I'm tentatively planning to do both of those at Jefferson, but I'm still in discussions with Meredith about possibly doing one of those a week at Kennedy, or occasionally doing one at Kennedy, but it might just be easier to just do it at Jefferson. And so I'll talk about that later. But those high school office hours are Mondays and Wednesdays from 3 to 4. Your school basically ends at 3, right? So that should work out pretty well. And at Jefferson, I do them in Meredith's room. So you can just come down there. The way we ended up doing it by the end of last year was I would usually just write problems up on the board, give students some time to work on them, and then I would work through the solution to compare to their solution. And that's another place where if you have questions about specific problems on the homework or whatever, I can give hints or work through it or whatever. This is the textbook. Since you guys get the textbook for free, you might as well have a textbook. But and you can use that as a supplemental reference. But this class is going to be totally self-contained. You could do this class perfectly fine without a textbook. I'll give you everything you need. I'll tell you everything you need to know, and then I just expect you to read my notes, read the notes, reread them, remember what I said, you know. The way I kind of think about that, so this kind of class without a textbook thing, I think about it this way. It's sort of like I give you something, you give me something. So I cut way down on the number of pages that you're responsible for. You know what I mean? Like all of the, hello. Hi. So if you typed out everything that's going to be in all your notes the whole semester long, typed it out in the size of font that textbooks use, it's not very much text, right? So it's a lot less text than like in a normal class where you might be responsible for 100 pages over the course of the semester or something, way, way less. But so the trade-off, the thing I want from you is so I'm trying to condense the amount of information way down, and the trade-off is I want you to know that information in more depth, remember it better than you would in a class where you were responsible for 100 textbook pages, So it doesn't take much time to skim through all the notes in the class, so I expect you to sort of keep refreshing that, and I'll talk about the ways that I'm going to sort of check that as we go. Anybody have any questions yet? Recommended books. I don't know if you guys have discovered the magic of Sham's outlines yet, but it's like the greatest thing in all of science. There's this book series called Sham's Outline. It's these red and yellow and white paperback books. They cost like $15 to $20 each. So, like a textbook costs $200 or something. This costs $15. And it doesn't have wordy descriptions of things like a textbook does. It has real concise summaries of the topics that are nice if you've already taken the class. You might not want to read everything in so much detail. You might just want a little refresher about the main points. It's good for that. And then they all have, I think, literally thousands of problems. Pretty much all of the problems have answers in the end. Some of them have full solutions. So it's just a great way to, if you're ever getting ready for a standardized test or trying to refresh your memory before you start college or whatever in a couple of years, it's just a great way to prepare for, remind yourself how to do the problems. And yeah, $15 or $20. And actually, a lot of them you can find for free online. So You can always Google it, but basically I think every science class you take from now on, you should buy the Shams outline. Why not, you know? And then I think the majority of the class, if it's like last year, is going to take the AP test at the end of the year. So this is a good reference for getting ready for the AP test, cracking the AP Physics C exam, Princeton Review. So that's the one that you're going to be taking is AP Physics C. And then you need a scientific calculator. The minimum you need is a calculator that does sine and cosine and tangent. But it would be better if you have a graphing calculator that does vector and matrix operations, just because of the kind of classes you're going to be getting into in the next year or so. And have you ever had a class where the word eigenvalue or eigenvector came up? That's going to be, for any of you who are thinking of possibly going in the direction of engineering or physics, that's going to be a big topic, eigenvalues and eigenvectors. And so if you're in the market for a new calculator, I would say look for one that does those. It's a nice time saver. The TI-89 does it. The TI-Inspire does it. Some of the older TI calculators do not. So like TI-83, 84, and 86 do not do eigenvalues. But the TI-89 and the TI-Inspire do. The Inspire is pretty slick. I don't have one of those. Do any of you guys have the TI-Inspire? That's sort of the newest, their newest model. It has really nice graphics compared to the other ones. It has a touch screen, which I don't think is that helpful actually, but that's sort of the new thing. So, and it does everything. Solar Edition. Prerequisite is Calc 1. Co-requisite is Calc 2. Like I said, I'm going to tell you all the calculus anybody ever needs to know in 50 minutes today. All the rest of that time you spend is a waste of time. And everything that I give you, every material you need is going to be given on D2L. So I'm doing all my lectures on a computer. You saw what it looks like when I write up here. As I'm doing this, I'm recording a video too. So let me show you what we're going to get from the lectures. This is a really useful reference to have, especially if you miss a day of class. So let me see if I can find one. After the class is over, I can make a PDF of the lecture. I can and will. So let me do one from last spring. So when the class is over, you'll see a printout like this. I've gotten a little... You know what's annoying is I'm left-handed, and that's why all these things that make it look like a cheap mimeograph or something, like my hand's dragging on the screen. I used to, like my old low-tech computer only recognized the stylus, so now this is like a fancier one that recognizes touch, and so I get smears all over. Ah! Being left-handed, I don't recommend it. And so on D2L, I'll post PDFs of all my lecture notes. So if you ever miss class, or even if you're in class but you miss something in your notes, you can go back to this as a reference. Okay? And on YouTube, I haven't created the playlist yet for this semester. Let me see if I can get sound coming through the system. Those aren't mine. Okay, so. Oh, you know, I have all this Five Nights at Freddy's stuff. It's not because I'm like a weirdo. It's because I have a 9-year-old son who's always watching Five Nights at Freddy's. Okay, so physics with calculus. So this is from last spring, and there's going to be a playlist of all the lectures. And so here's what it'll look like when you go to one of these lectures. See if there's any volume. That's not so interesting. Okay, well, I don't know. I can't get the volume to go through, but my voice in these videos is going along with me writing. So it's basically just like watching the board and listening to the lecture. So if you miss a lecture, you can go to that YouTube playlist. I'll put a link to the playlist on D2L, and you can watch the lecture here, take notes like you were in class. And actually, if you miss the class, it might even work better to print out the PDF of that day's notes. And then you can watch the video and just sort of make your own notes in the margins, but all the main body of the notes is already there. Oh, that was the fake. Okay, how do I get out of here? Here are the topics we're going to cover. I'm not going to go into that right now because that kind of the wording probably wouldn't make a lot of sense. But these are the topics we're going to cover if you're interested in Googling anything or anything like that. The grading scale is a little on the high side, maybe compared to the classes that you're used to. My thinking on this class is I try to be very clear about what's going to be on the tests. The problems on the test are very similar to the problems I'm going to give you in homework. There shouldn't be any surprises, so if you're doing the homework, spending the time that you're supposed to, you should be able to get pretty much everything right. And so the grade cutoffs are 92, 82, and then for a C, which I assume no one in here is too excited about anyways, 70, and so on. But yeah, I mean, I really think B's for sure, and even A's are very achievable if you can find the time. Like my experience last year said, the key is finding the time, and I know that's hard for you. I mean, the schedules you guys are doing are I've never seen schedules like that, so I know that's hard. But if you can find the time, I think you'll do really well in this class. Your final grade, 40% of your grade is going to be based on tests. 30% is going to be based on assignments. Lab exams, 20%, and quizzes, 10%. So let me just go through these 4 categories. There are going to be 4 exams. So each one of those is worth 10% of your grade. The exams are going to be all problems, so there's not going to be any questions about like remembering stuff from lectures. It's just going to be doing problems. And the problems are going to be based on the problems that you get in your assignments. So they won't be the same, but they'll be the same thought process. And yeah, I think if you if you do the assignments thoughtfully, when you get to the exams, nothing will be a surprise. I think it'll look very familiar when you get to it. The dates of all the exams are given. If you can't make an exam, I know you all have extracurricular stuff going on and whatever. We can work around that. Just let me know as soon as you know that you're going to have trouble making an exam, and we can come up with a makeup. Each exam is worth 10% of your grade, so none of those is like a really huge, important thing, but they add up to the biggest chunk. Assignments, yes?
Oh, I was just wondering, is your final like counted, like is it like a test? Is that how you do it?
The final, yeah. So that Friday, May 5th is the final. One thing I should say about the exams is all of these exams are cumulative up to that point. So like exam 2 won't just be the stuff from exam 1 up to exam 2. So I'm going to try to give assignments that are going to make you refresh your skills on the old stuff, you know. But yeah, I expect you to keep going all the way back and reminding yourself about the old stuff. In a way, a lot of this class does that for you because the topics build on each other. But okay, assignments will be given daily, and they should be turned in at the start of the next class. I don't know about Thursdays. We'll see about that. Maybe I'll give short assignments on Thursdays since the next class is Friday. You know, we have this weird schedule where I see you Tuesdays, Thursdays, and Fridays. It's like basically like the class is Tuesday and Thursday, and then labs are Fridays. And it says something about the solutions. It says there's full solutions given for many of the problems, most of the problems, but you should always try to do the problems yourself before using the solutions. Okay, and this is sort of a wacky thing that we're going to try, see how it goes. To really understand these problems, I've always said in the past you need to do every problem at least twice. So now for the first time I'm like, well, I might as well make you do it twice. So it seems sort of stupid, right? I know it seems sort of stupid, but I'm going to assign the problem, you're going to turn it in, and then later I'm going to assign the same problem again, and you're going to do it again and turn it in again. You're not going to turn in the same one. That's not, you know what I mean? You're going to do it again and turn it in again. And the second time that the problem's assigned, what you want is you want to be able to go through it smoothly. You want to understand it easily. Your goal, like I would say, you understand a problem when you could explain to somebody else why you've made each choice at each step, you know? Like, and someone could say, like, I don't get why this is negative, and you could say, like, it's negative because this is moving in the negative direction, whatever, you know? If you can understand the problem at that level, then you understand that problem the way I want you to. So the second time you do it, you should have that understanding of it. Sometimes you won't, and if you don't, that means you need to spend more time on that or revisit it again later. I'm not going to assign anything a third time, but it's very reasonable to do problems more than twice, you know. You're just trying to ingrain these skills. So yeah, if the second time you do it, if you need to look at the solution or look at your old solution to figure out how to do it, then you need to, that problem's going to need more work before you're ready for exams and stuff on that material. Okay? And then lab exams. My labs are also currently a little bit wacky. We will do a small number of labs where you're actually like taking measurements and you know, the way you think of as a lab. But most of what we're going to be doing are kind of intuitive exercises just to build your idea of like what direction this thing's going, what direction is the acceleration, what direction is the force. There's going to be a lot of just drawing approximations of vectors. And so you're going to do these exercises in lab, and then 3 times over the semester, you're going to have to answer problems similar to the lab questions in a test environment. And so there's the schedule for the lab exams. Just the same as the exam schedule. Please, as soon as you know that you're going to have a conflict, let me know, but we can work around that. Those lab exams are worth 20% of your grade. So each one of these lab exams is worth, what, 6 2/3 of your percent? So each exam is worth 10%, each lab exam is worth 6 2/3%. And then the last thing that goes into your grade are these quizzes, these weekly quizzes. Every Friday, the lab day, we'll start with a short quiz on the homework assignments since the last quiz. So the homework assignments over the last week. And the homework assignments are always going to, first it's going to tell you some stuff that you're responsible for reading. Those are just your notes, but you're going to be responsible for reading the notes, looking back over the notes from that last day. And often, usually, you'll also be assigned to look through the notes from some previous day and a set of problems to do. And these quizzes will have questions about the notes that you were asked to read over the last week, and then they'll also ask you to reproduce problems that you did in the last week, just to make sure that you're, internalizing this stuff as you go. So nothing you haven't seen before, but just making sure that you're paying attention as you go. So there are going to be, somewhere close to 15 of those quizzes. That's only worth 10% of your grade. So each quiz itself is worth a very small percentage, but they add up to, a full letter grade, basically. And then this down here says you should not cheat in this class. I don't know what the policy has been on cheating in the other classes, but I discourage it. That's all. That's all I have to say about cheating. I bet some of your other professors are like, I admire your ingenuity or whatever, but I'm not really like that. I just sort of don't want it. Okay, anybody have any questions about the syllabus? Or any questions about the class overall? This class ends at 9:35, I think. Is that right? Yeah. All right. So, yeah, maybe we're going to do 2 semesters of calculus before class is over today. It's going to be, this is going to revolutionize your thinking on calculus. Yes?
For the labs, are they at 7?
The lab starts at the same time as regular class, correct?
They start at the same time, yeah. That's early. I can't get up that early. I'd have to give you the keys.
Neither could we.
Yeah. No, let's not do it this Friday.
Okay, because I like calculus.
Okay. Okay, calculus in 1 hour. Calculus in 1 hour is my most popular YouTube video. I got 1 comment on it once. Okay, so calculus is about two operations on functions. Derivative and the integral. Hopefully this, nothing yet, is news. You're really lost if you didn't know that much. These operations are related. What's the thing called that relates derivatives and integrals? By the fun. Dimental. Theorem of calculus. That says they're inverse operations. Or in other words, one undoes the other one. I said that these are both operations on functions, and both of these depend on the fact that there's a functional relationship. So let's say the function relationship where one variable is independent and the other is dependent. You know what the biggest downside to Dimensions Academy is? That none of you are going to get to take math with Sean Foley. Have you ever heard of him before?
Yeah.
Holy moly, that guy is smart. You should just like hang out outside his office and try to just soak up whatever you can. That's my advice. Even though you're not in his class. Okay, so for example, f of x is equal to x squared minus 2. In that case, x is the independent variable. And f is dependent. And you can tell because it says that that's what this function notation says, is that this f is dependent on the variable in the argument. And a relationship that we're going to see all the time is one where the independent variable is time. So x of t is equal to cosine t. In that case, t is independent. And x is dependent. And to plot a function, the independent variable goes on the horizontal axis, and the dependent variable goes on the vertical axis. So for example, if you have the function x of t is equal to cosine of t, which one's the independent variable? T. And so t goes on the horizontal axis, x goes on the vertical, and then, you know, the graph looks like that. There can be, you know, function relationships between all types of variables, but in this class, there's mainly going to be two types. So in this class, there are mainly two types of function relationships. The first one is I'm going to say it like this, and then I'll tell you what this word means. So kinematic variables that are written as a function of time. These kinematic variables describe motion. So like, for example, position, velocity, acceleration. There are others, but they're all sort of in that same category. So some examples are like, if you think of x as the x coordinate of an object, you know, as an object moves around, its x coordinate changes if you're tracking it in a coordinate system. And so there's a different x coordinate at every different time. And so you could write the x coordinate as a function of time, like, you know, maybe for some particle it's represented this way. And you could also do the same with the y coordinate. So you could write y also as a function of time, say negative 5t plus 6. You could also do that with like velocity, like how much of the velocity is acting in the x direction, how much is acting in the y direction. So you could write it as the x component of the velocity, that's a vector thing that we'll get into in detail, is equal to 3t, and the y component of the velocity is equal to negative sine t. Okay, so that's the first type of function relationship that we're going to have, where the independent variable is time and the dependent variable is some description of the motion. And then the second type that we're going to have is a variable that deals with speed in some way, given as a function of a position variable. This type of relationship is going to come up when we talk about energy. And I think it's useful to start keeping that idea in mind, because when we get to talking about energy, we're going to get to, it's going to be the first time that we get to problems that we could actually, that you could actually approach with a technique that we'd already discussed. Okay, so all of a sudden here, things get a little hazy on like what way to go. You can look at a problem and use the wrong techniques or techniques that make the problem harder because you have multiple options. But this is a association to make with energy problems. If you have a problem that's relating speed to position in some way, you're probably going to want to use some kind of energy approach. So for example, 50 times the height of an object is equal to 10 times capital V squared, where this capital V is the speed. This h is the height. And so you can solve this problem for v and write it as v of h is equal to, well, plus or minus square root of 5h, right? That's just solving that problem. And then since we're talking about a speed, like how many people here have cars with speedometers that go negative? Anyone? I just want to make sure I'm right on this. Okay, nobody? Okay, right. So speed has to be positive then. Okay, that's confirmed again. Okay. So once this independent, dependent variable relationship is known, the derivative is the derivative of the dependent variable with respect to the independent variable. And the integral is the integral of the dependent variable with respect to the independent variable. Am I writing too fast? So for example, if f is a function of x, what's the independent variable? 50% chance? Yep. And the dependent is f. So that means we can talk about it makes sense to talk about the derivative of f with respect to x. And it also makes sense to talk about the integral of f dx. Okay? It doesn't make sense to talk about the integral of x df or whatever, because one of those is dependent on the other, you know? Or what's going to probably, in this class, come up more often, if x is a function of time, then we can talk about dx dt and the integral of x dt. So what about things, so this is just saying the only thing that the x coordinate depends on is the instant that you're talking about. What about things that depend on a whole bunch of variables? You know, that comes up in our life all the time. Like, for example, so what about a variable that's dependent on multiple variables? So, like an example is the weather is a function of, you know, how much sun there is, the atmospheric pressure, the time of year, right? A million things. So how does what I was talking about here relate to a case like this? Well, that's a class that's going to be coming up, like if you keep taking calculus, let's see, I think maybe that's the next one. I think that's Calc 3, is multivariable calculus, where you have multiple independent variables for a single dependent variable, and you have what's called partial derivatives, where you're taking derivatives with respect to a single one of those variables at a time. So that's coming down the pipe. Multivariable calculus. I think that's Calc 3. One important thing, notation-wise, is for f that's a function of x, df dx is equal to f prime of x, right? You've seen that notation before. This holds, or this notation is what you use for any independent variable except time. It would still, I mean, the notation still makes sense if time is the independent variable, but for time we use something else because It's so important in physics and engineering. If time is the independent variable, and let's say that we have x is equal to x of t, then dx dt is x with a dot over the top. So the dot always means d dt. All right, so now for calculating derivatives, I'm going to separate it into 8 key principles, the only things you're going to need for calculus in this class for doing derivatives. Who knows which kind of principle this is? You know, you can spell principle 2 ways. PLE, good. Yeah, exactly. That's how I think of it. Okay, 8 key principles for calculating derivatives. The first one is if you have a constant, you know, a number c, the derivative is 0. The second one is to take the derivative of a variable to a power. You do the power times the variable to the power of n minus 1. Okay, so for example, the derivative of x to the 4th, what's that equal to?
4x to the power 3.
Yep, 4x to the 3rd. Cute. And that works with negatives too. The third one, the derivative of natural log of x, what's that equal to? 1 over x, yep. I don't know, it was pretty close. Yeah, I couldn't understand either. Okay, the fourth one, I'm going to break this one into 2. This is the 2 trigonometric functions that we're going to use all the time. d dx of sine x is equal to? Yep. That's good. I always get the signs mixed up on these. And then d dx of cosine of x, what's that? Negative sine. Yep, good. Fifth, d dx of a constant c times some function is equal to the constant times the derivative of the function. Okay, so that's so this is where C is a constant. So like, for example, if you want to take the derivative of 5x squared, you know, that's equal to 5 times, yeah, I mean, you by now, I'm sure you don't think about this rule, you just do it in your head. But the way it works is you're pulling that constant out. It has to do with the linearity of this derivative operator. And you have 5 times d dx of x squared. And so that's 10x. Okay. But it doesn't, this ability to pull the constant outside of the derivative doesn't only hold for polynomials. It holds for any function, any wacky function you can come up with. Sixth, d dx of the quantity f of x plus g of x, what's this equal to? Yep, so df dx plus dg dx. And these two together, well, let me do an example of this. So d dx of 3x cubed minus 5x is equal to 9x squared minus 5. And 5 and 6 together combine these. This is the definition of a linear operator. So derivative is a linear operator. Any operation that satisfies these two rules is linear. So that's like, I feel like I kind of have two jobs for you. I have to teach you to do some physics, but I also have to teach you to like sound smart in like cocktail conversation or whatever. This is the kind of thing, like, you already knew this, but if you can slip the words linear operator into conversation, it's going to help with your college admissions and whatnot.
You know they're too young for cocktails, right?
Kitty cocktails.
Oh.
Yeah.
That was implied, yeah. You can still go to cocktail parties. Yeah. Okay, the next one. Now we're getting into the two best. Product rule. d dx of the quantity f of x, g of x is equal to the derivative of f times g plus f times the derivative of g. So for example, the derivative of the quantity x squared cosine x is equal to derivative of x squared. Well, let me break it down like this. So we're taking d dx of the function x squared times the function cosine of x. And so that's equal to 2x times cosine of x plus x squared times negative sine of x. So 2x cosine x minus x squared sine x. And so you might think the next one of these important things is going to be the quotient rule, but it's not. You should forget the quotient rule because you need that space in your brain for other stuff. Okay? The quotient rule is the product rule. You just have to think of the first function as being multiplied by a function that's 1 over the denominator function. You know what I mean? So like, here's an aside. There is no quotient rule. It's not a real thing. I know. The derivative of f of x over g of x is the derivative of, I need a lot of brackets for this, I think, f of x times g of x to the negative 1 power. And then you just use the product rule. And now you can use that brain space for other stuff. But you could derive the quotient rule that way. Okay, so what's the next one? If it's not the quotient rule. Chain rule, yes. That's the last one. So the derivative of f of g of x is df dg times dg dx. So, for example, d dx of sine of x squared you can think of, well, that's equal to this might make it more confusing than helpful. Let's see, but d dx. Okay, wait. So it's d of sine of x squared with respect to x squared, and then multiplied by d of x squared dx. So if x squared is a variable of its own, what's derivative of sine of x squared with respect to x squared? Like, it's easier if you think of this x squared as being a u or something, you know. Yeah, right. So this is cosine of x squared. This is 2x. And so you get 2x times cosine of x squared. Any questions about any of that? Okay, that's Calc 1. Yeah. Okay, so now integrals. How did I start this? Eight key principles for calculating integrals. How many key principles were there for calculating derivatives? 8. Yep, and each one of these 8 for integrals is going to exactly mirror one of the ones for the derivatives. Okay, I'm going to do them in the same order. And I'm going to do, I'm going to do this for indefinite integrals. And then after that, I'm going to just extend it to definite integrals. But pretty much everything I'm going to talk about is for indefinite integrals here. Okay, so the first one says for a constant c. Oh, no, I'm not going to call that C because C is going to be my constant of integration. Let's call this A. The integral of A dx is equal to AX plus C. Second, for n that's not equal to -1, the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus c. So, for example, the integral of x to the 4th dx is equal to x to the 5th over 5 plus c. So, what does that constant of integration mean? It means no matter what that constant c is, you can make that whatever you want if you take the derivative of this value you get the original function back. So 3, this leaves a gaping hole in what we're able to calculate, the fact that it doesn't work for n equals -1. And so the third one says the integral of x to the -1 dx is equal to the natural log of the absolute value of x plus c. Fourth, I'm going to break this up into 2. This is the sine and cosine one. The integral of cosine x dx is equal to what? Sine, yep. Sine x plus c. And then the integral of sine x dx is equal to negative cosine x plus c. Fifth, the integral of a times f of x dx is equal to a times the integral of f of x dx. So, for example, the integral of 5t cubed dt is equal to 5 times the integral of t cubed dt. So that is 5 times t to the 4th divided by 4 plus c. Who's getting tired of this? No one? Good. I was afraid you might be. We're almost done for the day anyways. Okay, 6th. The integral of f of x plus g of x, quantity, dx, is equal to the integral of f of x dx plus the integral of g of x dx. So, for example, the integral of the quantity 3u cubed minus 2u du is equal to the integral of this one plus the integral of this one. So that is u to the 4th over 4 minus u squared plus c. And the way the constants work is this is totally an arbitrary constant. So if you're dealing with multiplying these constants by something or adding these constants together, 2 arbitrary constants just give you another arbitrary constant. So I'm just calling that c. Yep?
Where'd the 3 go in 3 years?
3. I was about to put that in. I just hadn't done it yet. Okay. Thank you. Okay. And 5 and 6 together, how do you refer to those at a fancy cocktail party? Integration is a linear operator, that's right. Now that Meredith's gone, we can talk about cocktail parties again. Yeah, exactly. Number 7. What is the inverse of the product rule? Oh, you know what? I think now that I bet you haven't gotten to this yet. I bet you've never seen this yet. Okay. It is called integration by parts. Have you ever heard of that?
No.
You've heard those terms before, maybe? Yeah. That's not what I meant. So I'm not going to do examples of that or anything. We're not going to use that in this class, but this is just to say that there is an integration version of the product rule, and it works like this. If you break, I think this is how they're going to talk about it. I'm going to put it in quotes because when you get to this, you'll say like, yeah, I remember this. But you break an integral up into UdV, and that's equal to UV minus the integral of V du. That doesn't make any real mathematical sense, so you don't worry about making sense out of that, but that's the way you're going to learn it. What it really is just backwards operation of the product rule. And I'm not even going to talk about how they connect them. But if you want to know later when you get to it, I can show you if you ask me. And then inverse of the chain rule. This one, yes, very good. U substitution. So if you're taking the integral of a function of another function with respect to x, then du dx is u prime of x. That's not math, that's just notation. And therefore, you can think of multiplying the dx to both sides. Mathematicians would not like me talking about it this way, but physicists don't mind this kind of stuff. So du is equal to u prime of x dx. And so dx is equal to du over u prime of x. And so the new integral you can write as the integral of f of u du divided by u prime of x. and it only works when all the x's cancel out. So, for example, if you want to take, this is the last thing I'll do, and then you're free. So if you're taking the integral of x cosine of the quantity 2x squared dx, we'll make u equal to 2x squared. Then du dx is equal to 4x. You know, that's the u prime. And so now our integral becomes the integral of x times cosine of u du over 4x. This happens to be one of those problems where we get that cancellation. So that goes away, that goes away. And now you have the integral of cosine of u du over 4, which is negative 1/4 sine of u plus c. And then we were given this problem in terms of x, so we want to get that u out of there. So now just substitute back in, and you have negative 1/4 sine of whatever u was, 2x squared plus c. Okay, any questions about that? All right, so we didn't quite finish all of calculus. I have to talk about definite integrals, but that's going to take like 5 minutes, and then we'll go on to physics next time.